Thank you, Mr. Hamenos, for the very interesting speech. I would like to present Professor Dimitris Lalas. Professor Lalas is a renowned climate scientist. He has a lot of titles, but I cannot tell them all. I will just stay with one. He used to be for many years, I think, the president of the National Observatory of Athens. And today he will talk to us about science-based approach to risk estimates.
Thank you. Thank you very much. Thank you for the invitation. By the way, I'm not the only president of the National Observatory of Athens present here. I think the next speaker will also be. So mind you, okay, that's where we'll stop. There won't be a third one here yet. But you know, if you are kind enough to invite us again, we'll be back maybe to provide a little bit more information on whatever issues might be important, especially if they have to do with the environment and climate change. Change of age, possibly change of atmosphere, and I mean that in both senses. What I would like to do today is to try in 15 minutes, that's how much I was allotted, to give you a little basic stuff on the science and the methodology on at least the first part of the 3 words of the topic of today's symposium, namely the threat part. And I would like to present to you where the tools are that you use to calculate that and the methodology of that, and just mention a few examples of how all that stuff at the end finds out what the risks are and quantifies them so that the next step, which includes the possibilities of taking advantage of them or at least finding means to adopt to them in the best possible way, will come from. So if I understand that if I press that, the other way. Here we go. We're talking about climate. I mean, this is like, you have to start. And you cannot, if there is not a possibility not to show that curve, the temperature goes up and up and up. And mind you, we say Paris Agreement and how much we believe in it, 2 degrees by above pre-industrial level, we're pretty close to that, or at least way ahead to meeting that. And we're very close to go by the 1.5 degrees, which is something that we should make every effort to reach. Mind you, the many curves that you see on your left, on the large figure on the left, are estimates of where the temperature, the mean temperature are by a number of organizations around the world, so there should be no doubt that this indeed is what is the consensus of the scientific opinion on that particular issue. So it's there, it's coming, and as a matter of fact, if you look at what happened between 1950 and now, it's accelerating, and that's why if you look at the much longer term trend on the bottom right hand side, you'll see that it goes almost flat and then straight up, what's known as the hockey stick effect. And then the next thing, the IPCC calculations have already been mentioned, namely what happens in the future. And here are a number of estimates. The black line is where we have been, and the red line, or hopefully the blue line, is where we will be. And the question is, where do these estimates come? And furthermore, how do you use these things? As a matter, the title of the symposium today says increase. So the question is, how do we take that general stuff that affects the whole planet, and it does affect it, and try to make sense and use locally? Here's where the science comes in. As you can see, trying to figure out what happens in the atmosphere is a very complicated thing. The processes, the number of physical processes and chemical processes and geological processes that are involved are numerous. And if you're trying to find out what's going to happen in the future, you have to be able to build a model that takes into account all those features, and including the interactions and feedbacks there. And indeed, as good scientists, we started a long time ago, 1890, and we have started building models, and every decade or so, they get to be a little bit more sophisticated. Meaning that you introduce more processes, and you introduce more details to make sure that the models that you have are indeed as accurate as they can be with the resources you have available, and I'm talking about the measurements you have available, and the computational resources and the scientific resources you have available. And indeed, as you can see, every decade or so, another process has been added, and we have reached a fairly high level of sophistication, and hopefully a level that we can really trust the results. This is not, though, a process that just involves physical and chemical science. Because what's going to happen in the future will be a result of what the emissions will be in the future. So that if you're going to run a model, a physical, meteorological, climatological model, of what's going to happen to the temperature of the planet and has its effects and impacts in the future, you need to know what the concentration of the greenhouse gases are in the atmosphere in the future. How do you do that? Well, you say, we, anthropogenic, right, are the people who are going to be producing emissions which will increase the concentration in the atmosphere, and that increase in the concentration in the atmosphere will affect temperature, precipitation, and so forth and so on, impacts, damage, and hopefully means to address them. So, as you can see, it's a circle. You need to know what kind of emissions you have to be able to predict the temperature, to be able to estimate the impacts and the damages. So where do you start? Well, that's where the situation started to get a little bit more complicated, and what happened was that that particular circle has been used in a number of situations, and as future comes along, you try to use whatever information you have available and whatever techniques you have available. So the way to do that is to say, let me isolate things. Let me isolate the physical part, which is the blue thing over there that says climate change, right? And where we know already that you need to be very sophisticated on how you handle it, and try to model the rest of the circle. And so what the process was to say, let's forget about the details, the specific details of the physical processes, try to simplify them as much as possible, and try to then use that, having simplified a very difficult part, try to see whether that particular circle can be estimated. In essence, what we're talking about is a vision of the society and the activity, economic activity, physical activity of the future. And clearly that means a lot of uncertainty. And how do you do that? You devise or you put together scenarios of how things will evolve in the future. And since you really don't know how things will evolve in the future, you don't build just one scenario, but you build 4 or 5 or 6 scenarios, and then try to say, well, look, if we go that way, we will be there, that is, we're going to have that many emissions. Those emissions will affect the climate will affect us, and that might possibly affect also how many emissions we'll be doing in the future. That particular circle, the scenario circle, is then used, because now we know the concentrations, in the more sophisticated scientific model to produce estimates of what the real physical changes will be in the future. So here are some scenarios. And when I said you built some scenarios, this business started in the 1990s. And every decade or so, those scenarios get to be a little bit more sophisticated, a little bit more complete, a little bit more in a way that includes a number of parameters. We're talking about now social parameters and economic parameters. And you can see some of those parameters, for example, whether the economies at an international level will converge, whether the median GDP will grow or not grow, whether the population will grow or not grow. And you have 4 different, in this particular case, families of scenarios. A scenario that says, we'll go right ahead, we'll continue what we're doing, we're going to burn everything we can get our hands on. Another scenario which will say, no, we'll be very much circumspect, we'll use circular economy, we'll do all we can to be green. And something in between, yes, a little bit of that and a little bit of that. And the axis on the thing, you can see that here's the scenarios with environmental emphasis, the regional emphasis, local solutions, the global emphasis, global solutions, and the economic emphasis in the particular scenarios. Based on those scenarios, we run the model, and then we calculate the emissions. And from the emissions, we go ahead and use the sophisticated physical model to calculate the changes in climate. In the last 10 years or so, there has been another effort which says, don't do that in the way I just described, which is on the left side, but in between, try to make sure you account for the interplay between all those things while it's taking place. So you can see on the right-hand side, you go back and forth and say, well, if I go and do that, still with a circular, simpler model, I will have some reduction locally, and I will have some possibly reduction of the emissions. For example, if society changes its behavior and all of a sudden starts eating less meat, as the minister suggested, and Mr. Zorner's daughter made him do, right? Then that particular aspect should be taken into account as we try to put together concentration scenarios to be fed into the physical model. That's another level of sophistication to be added so we can have a little bit more security in what the results are. And the latest scenarios that have been used are here. Too many details, but in essence they follow the same philosophy. One, go ahead as is, burn whatever you can. The second is everybody's green. We're trying to be green as much as possible. And two in between, with the basic parameters of what do you do with the GNP and what do you do with population, still being major thrusters of where we're going to be in the future. Those scenarios are the ones that have been used in the latest impact assessment report of the IPCC, the Intergovernmental Panel for Climate Change. In the latest report, which was the AR5, right before Paris. In the meantime, though, and actually before that, scientists being scientists continue, and scientists I don't mean just physical scientists, but also economists, continue to produce advanced scenarios, and the latest ones to be used, go back. In the next assessment report, which is the sixth assessment report, to be published maybe 3 or 4 years from now, have included what I just said, the mechanism by which society acts and interacts to what it sees, and whether social patterns change that might affect our behavior, might affect then the emissions, which may affect the concentration. So with that in mind, 3 minutes. Okay. Now, in this particular circumstances, what you do is you start speaking much faster and But in any case, the results of this process were the concentration emissions that you see over there, a number of scenarios, you said, the old scenarios, the new scenarios. Is there any indication that this process is good? Here are the results. The second column from the left, the first column is the dates, the second column from the left is the simulation. The third column from the left are the actual values of the emission concentrations. So you can see that things are pretty close to what they have been, what you can measure anyway. But that scenario that says RCP 8.5 is the business as usual scenario, and it's not a very good scenario. A whole bunch of climate models now, we're going back to the physical part of it, have been used to calculate climate parameters for the whole planet. For the whole planet. So how is that going to help me to find out what's going to happen to the cultivation of wheat in Thessaly? Well, what you do then is you take the results of these global models and try to downscale the formal work, those results to a much local level. You do that in 2 ways. First of all, if you look at how the global models have progressed in what's known as spatial scale, you can see that as more resources have been put into the process, the computational capabilities have increased, and the global models have gone from a spatial scale of the best special scale being of the order of 300 kilometers by 300 kilometers, in which, if you have a topography like ours, Greece is almost flat, right? And then in 2004, it went down to a much finer scale, and now we're talking about the global models being of the order of 100 kilometers. But again, in Greece, in 100 kilometers, half of it is sea, half of it's 1,000 meters high mountains, and you can see in the picture how the topography itself, as represented in the model, becomes much more distinct and clear and much more accurate. And then you take those results, and you use what I just said, this downscaling thing, and try to use a different kind of model, which is called a regional kind model, in which the spatial accuracy becomes much better. Can go down to maybe 10 or 15 kilometers. And then, now you're talking, right? The results with the global model in what happens in our neighborhood, with the number of the scenarios that I showed before, the 4 scenarios, right, are shown there. This is for temperature. We're hot and we're getting hotter. And here is precipitation. We are not being very wet and we'll get even drier. Both of those things are very difficult things to handle, and the impacts are going to be substantial. But as I said, let's see whether we can calculate those impacts. And I know I'm now in minus 2 minutes in my speech, and I'll go faster. You can see now how much the accuracy is if you go from 200 kilometers to 25 kilometers to 1 kilometer. And indeed, for all those climatic parameters, which I'm not going to enumerate, now you can get down to 11 kilometers, and that's those kind of maps of the temperature increases in Sterea Elada have been worked out with 11 kilometer resolution, right? And you can start saying, okay, now I can start looking at what the impacts of those particular climatic scenarios, if the scenarios of how the economy and the population and so on will evolve in the future, will be in that region, which goes back to the adaptation plans that the minister mentioned about, because this was indeed done in the process of putting together the adaptation plan for Sterea Elada, and you can indeed find out what the damage is. This is precipitation, the same region, and you can see, you can use the same now detailed information to calculate a number of effects. For example, the one on the left is focused on the impact of on the agriculture in Greece, and the one on the right is something that governors general should be interested, is to see what the risk of one particular systemic bank of Greece is to climate change related risks. And by the way, in both of these studies, which were published a couple of years ago, research scientists from the observatory have been playing a very strong role. Now you can see that the methodology, after you have taken now the climatic variable changes, you need to make that into an estimate of what the real damage is. So quickly, I'm not going to go through the methodology, but what it says is, take these changes, translate them into vulnerability, take the vulnerability numbers, and put on it the relative change compared to some particular temperature changes or precipitation change that you know. For example, we know thermal power plants' performance decreases by 0.5% per 1 degree change of the environment. So you can calculate what that impact is, and so at the end you can come up with a risk for the particular activity, and you can do that for all the activities. Again, this is actually from Eastern Macedonia Thrace region, and you can do that for all the activities that the Elstat reports statistics on, and you can rank them, and so that at the end you can get out to the map. This is the intensity of impacts per scenario, 2 scenarios. One, what's seen there as RCP 4.5, which is the middle of the road scenario, and the 8.5 8.5 scenario, which is burn everything scenario, or actually not burn everything that we're doing today. And you can see a map of which particular activities are in danger, which particular activities are in smaller danger or risk, and some activities that you can ignore because indeed they are not in that much of a risk. And by that, you can follow up with putting together an adaptation action strategy for each region, which might be the way to go ahead and plan policies and measures afterwards. I've already exhausted my time, and this is my last slide. And mind you, impact, right? This is the other side of the one I started with, Pinhos River, which is just flat and no water. But that goes back to being a low slide.
Thank you, Professor Lalas, and thank you for keeping the time. You've been the most accurate speaker up to now, I think. And I would like to, and Mr. Family as well, I'd like to say, he was within his time. And I would like to welcome Professor Emmanuel Plionis, who is the current Director of the National Observatory of Athens and President of the Board of Directors. He's also Professor at the Aristotle University of Thessaloniki. He's an astrophysicist, but as the president of NOAA, he will talk to us about services and infrastructure related to forecasting, localization, management, and mitigation of climate change and the related hazards. Let me start the presentation. Yes.
Thank you very much for the invitation, distinguished guests, ladies and gentlemen. I'm here, as you heard, not as a cosmologist, because within the astrophysical realm I do cosmology, but as the Director of the National Observatory of Athens, I will try to present to you the various services that we have developed based on the research done at the National Observatory of Athens regarding forecasting, localization, management, mitigation of climate change-related hazards. These are not the only hazards with which we are dealing at the National Observatory of Athens, but due to the specific title and the theme of this symposium, I will only concentrate on these hazards. Right, a few words just to present the National Observatory of Athens and for which reason actually I stand here in front of you. This is the oldest research establishment in Greece. It was founded just a few decades after the liberation from the Ottoman Empire in 1842. It has a functioning constant in time, and today it consists of three institutes: the Institute of Astronomy, Astrophysics, Space Science, and Remote Sensing, the Institute of Environmental Studies and Sustainable Development, and of course, you must know about this very well. Recently, there's a lot of TV programs regarding this. The Geodynamics Institute, which is responsible for the monitoring of this seismic activity in Greece. Now, the National Observatory of Athens operates an extensive network of research facilities throughout Greece, and also a lot of spaceborne facilities which we have access to, as well as we have developed a lot of analytical and numerical models and information analysis algorithms to deal with large, huge amounts of data. Of course, we have the reason why I will give you this talk is the specialized and innovative services that we provide towards the state and the public. And it is interesting to say as well that we host the UNESCO Chair on Natural Hazards, and of course, as I said before, the National Seismologic Network and the National Tsunami Center. It is interesting also to say that we are participating in three related postgraduate programs. One is regarding space applications, the other one regards the environmental effect on Greek antiquities, and the third regards natural hazards. Recipients of our services are a lot of public sector organizations and ministries, OASP, the General Secretariat of Public of Civil Protection, Fire Department, and many others. And just to give you a potpourri of what we actually, the amount of infrastructure that we have developed through the years, I will present here the map of Greece with all the stations, the sensors that we have, which are, just to give you a list of them, 390 meteorological stations, the largest network of meteorological stations in Greece, 46 seismographs, 141 strong motion detectors, 24 GPS stations, 8 radon gas stations, 16 tide gauges, 8 magnetometers, 4 telescopes, 1 ionospheric station that integrates all the ionospheric data from Europe, radars, LiDARs, atmospheric chemistry laboratories, which are also mobile, 2 UAVs, and so on and so forth. Furthermore, we have a lot of space-based research infrastructures. We have, as you see down to your right of the view graph, we have radars and antennas that collect data from polar orbit satellites, geostatic satellites, as well as low orbit satellites like the European cluster, satellite cluster of Sentinels. Right, here we are. On the basis of this development, we have the Sentinel Hub. Greece, the National Bibliotary of Athens provides the international community, one of the hubs that provides the international community with the data of the Sentinel cluster. And our client, so to speak, is NASA itself and other space agencies from other countries. This is, in the photograph, you can see the operation center of the Copernicus Data Hub, as I just said. And we distribute on a daily basis. This is a service of 24 hours, 7 days per week, 365 days per year service, and we distribute daily 55 terabytes of satellite data. Right, now let's go and see and focus a little bit on the particular services that we provide the state with and the public. One is based on the Meteo unit. It's very well known. It has developed the network I just said before of 390 automatic stations throughout Greece, and it provides tailored weather forecasts, lightning and storm forecasts, wave forecasts, UV radiation forecasts, nowcasts, and dust forecasts. And in fact, we are the provision of the World Meteorological Organization regarding the dust forecasts. Furthermore, we have the lightning detection network ZEUS, which has, I think we are the only research establishment, public research establishment in Greece that we have detectors outside Greece. We have sensors in Spain, UK, Denmark, Romania, Cyprus, Egypt, that helps us to provide this service to the public. It's open data, of course. And just to indicate the amount of visibility that the Meteo group has, about 350,000 users daily. We have these hits in our web page. Right. Something which is very important, I think, and it's interesting for you to know, is that we are intensely working on providing to the public, actually the public authorities, a real-time rapid response forest fire forecasting system that can be used by the fire department in order to see how the fire that starts, a forest fire starts, how it will develop, how the front will develop. In order to do so, we have to have a detailed, real-time monitoring of the surface meteorological conditions as an input to the program. Therefore, our extended network is a prerequisite in order to be able to develop such a model, an algorithm. Of course, we need the detailed topography, the fuel type, that is the type of trees, the density, and so on. We need to know the ignition location. That's why we collaborate with the fire department to give us the precise ignition location. And then this model, this algorithm actually it uses at the same time the effect of the fire and how that changes the meteorological condition itself. So it's a loop that corrects the meteorological conditions by the fire itself. So this is a novel approach, It is almost ready. We have been we're sending it out for a publication in International Journal, and we will be ready by summer, I think, in order to provide the state with this tool. Just to show you that we ran it yesterday on the Strofilia fire, and we had, from what I understand, because I'm not a specialist, we have a specialist here among us, the group of Meteo. They told me that they had a very good correlation between the model and the fire itself. Now, the services that we can provide that can help the civil authorities are many. One of which, of course, is the fact that we have a very dense meteorological network in Attica, and this is exactly what allowed us to understand, to decipher the physical conditions, the natural conditions that created the disaster in Mati, because you need to have a very detailed measurement system in order to understand the local effects. And we have that. We provided this with the state with a study on that, and of course we can provide other real-time products on rainfall estimate and so on. At the same time, it's very important in order to study the vulnerability of different regions in Greece, something that Professor Lala spoke before, is to have a historical database of the floods and of different hazards that have hit different parts of Greece. And we have developed such a very detailed database, and you can see on the map at the lower right of the view graph, you can see the most susceptible regions of Greece to hazards, and the type of hazards are in the cycle in the pie diagrams. So you see that Thessaloniki and Attica, which are the most densely populated areas, are susceptible to hazards, and mostly to flash floods, as well as, of course, other hazards. So it's a very important. History can give us a lot of direction and a lot of important information on how to plan mitigation measures. The second very important center that we have developed in the National Laboratory of Athens is the Beyond Center. This is based on remote sensing, satellite remote sensing data. As I said before, we have antennas that we download a lot of data from different tens of satellites per day, every day. And on the basis of this center, we can actually have a real-time monitoring of natural disasters, from floods, landscape, fires, tsunami, whatever you want, whatever exists as a hazard, we can actually monitor that. And the area that we cover is East Europe, Mediterranean, North Africa, Middle East, and the Balkans. A very important service that we provide since 8 years at the fire department is the so-called Fire Hub. It's a space-based hub for fire management. We scan Greece every 5 minutes, so this is an ongoing, everyday process. So every 5 minutes we have the ability to detect forest fires and provide that information to the fire department. Actually, the fire department has this system. We have installed this system in the fire department, so they can have directly the data that we provide. The interesting thing is that although the static satellites have a resolution of 2 by 2 kilometers, we have managed with algorithmic processes, for which we got also a patent, to reduce this resolution to 500 by 500 meters. That is a 16 increase in resolution by algorithmic processes. And also we've got the monitoring competition best service. In 2014 we were awarded this for this service. Now, based on the excellence that we've developed in this direction, we've been awarded this year the European Forest Fire Information System to develop together with DLR, the German space agency, and now we are covering the whole of Europe, North Africa, and the Middle East at the everyday level. 6 times per day we scan Europe to detect fires, and 4 times per day we scan these fires to map the burned areas and provide the European Commission with its data. Finally, this group also can prepare products based on the expertise that has developed regarding the vulnerability and the risk assessment and mitigation planning services. And it has been called upon by 20 civil protection authorities throughout the globe, from Latin America, Africa, and Europe, to provide this data. Now I will pass to the last service I wanted to provide, to discuss with you. It's not the only one that we have, but I just selected a few just to give you the extent of the work that we're doing in this direction. This is an emergency notification system for extreme temperature within rural or peri-urban regions. This is a system that has tried to deal with the urban heat island, as it's called. That is the effect of when you have a heat wave, the interaction with the sort of buildings, the sort of material that you have in a town can increase these effects. And we've developed an applet that can be used by citizens, and it's based on satellite data, and it estimates the temperature, humidity, and discomfort index for every square kilometer of the city. And it provides estimates every 5 minutes. So this is again a service that has been used by Athens, Paris, Rotterdam, and Mallorca up to now. We've been called to provide the service to these towns, and in 2019, this summer, we have been called by Lisbon and Milano to provide the service. Finally, to close up my presentation, I think I'm on time, right? We are not only interested in providing services that have to do with the effects of climate change, or effects that are related to climate change, directly or indirectly, because all the previous hazards always existed. But the intensity and the frequency of the hazards is something that is related with climate change. So we do a lot of research, basic research on these issues, and in order to provide the research community, but not only, also the public and the state with necessary data, we are developing a new infrastructure for the National Observatory of Athens. I don't know if you've heard about it. There's been various publications in the newspapers. The Pangea Observatory of Geoscience and Climate Change, which will be located at the Antikythera Island. This is an important positioning of this infrastructure. We need to have the measurements of the climate parameters of the greenhouse gases away from the anthropogenic causes, anthropogenic pollution. So we need an area which is characteristic of this region, the southeast Mediterranean, but not affected by anthropogenic contamination, and therefore this was an excellent choice. You should imagine that other countries create islands, artificial islands, in order to have such observatories, and we will have a constant monitoring of climate and atmospheric parameters, as well as of in situ greenhouse gas estimates. And this will also contribute to the national obligation according to the Paris Agreement on Climate, the fourth assessment of the Intergovernmental Committee of Climate Change, and the EEC thematic strategy on air pollution. This is a project that's been financed, it's been supported by the Greek state. We have managed to convince the European Investment Bank to provide a big loan, together with public expenditure that the state has agreed upon. It's going to be a 20 million euro investment, together with about 3 million from the Perfect Slovakia, which they have agreed to support us in order to build the necessary infrastructure, buildings and platforms that we need in order to install all the instruments and the experiments. And with this, I finish my talk. Thank you very much.
Thank you, Professor Pioli. Now we would like to invite Mr. Nikos Karalabidis, who is the Executive Director of Greenpeace Greece, to give us the different side of the story, maybe, or a different insight on the problem we are talking about. So he will talk about people, I guess, citizens, our voice, the voice of everybody, and he will talk to us about, the title of his presentation is 1.5 degrees Celsius, what does it imply for us all?
Let me first congratulate the organizers for the courage in putting the brain and all the energy to organize that, and having the courage to put such a delicate and such an important and urgent issue on the table. I assume you will need to have much more opportunities to tackle that from different angles. We have enough science so far. Let me talk about history. First of all, that's fine. There's a long history around climate change. We've been talking about climate change for over 30 years. The first time that was a first global agreement on to tackle climate change, the Kyoto Protocol, that's 97, Dimitri? 92, we've been discussing the first non-legally binding agreement was 97, and since we're talking. So there's two ways of looking at this reality. One is that we know what we're talking about. The other is that we've been spending 20 years on talking. So keep that in mind, that we need to act differently. We end up 2015 with Paris Agreement. That's an agreement that is setting the pace for keeping temperature rise well below 2 Celsius. Keep in mind that the second part of the phrase, and if possible at 1.5, because this will lead us to the October 28 report. The agreement accepts reduction commitments. There's a mechanism that says how often the parties will meet again and again in order to see how they meet targets and if they need to renew the plans and set anew and whatever. We're talking about the need for reach global peaking of greenhouse gas emissions as soon as possible and to undertake rapid reductions thereafter in accordance with best available science, and achieve a balance between anthropogenic emissions by sources and removals by sinks of greenhouse gases in the second half of the century. And they've been requesting the Intergovernmental Panel on Climate Change to report back on what does 1.5 increase exactly imply. And here it goes. We come to October 2018, and we have the result, which is not fun, which is not nice. It says that there is a huge difference between 1.5 and 2 degrees Celsius increase temperature. You need to get into that report, and I mean it's a must read. The difference between the two is massive. Is massive. I'll try to depict that later on. In order to have a probability higher than 50% to remain close to plus 1.5 Celsius, humanity should achieve net zero carbon by 2050, the latest. Given the fact that most of the energy plans, the energy planning is talking about the next 30 years, that means that what we do today is impacting that, so we don't have a day to use. Next year's, even more important, 2030 seem to be the most crucial, where we need to achieve reduction by 45 to 60% of CO2 equivalent emissions. You see a quick comparison of what does plus 1.5 and plus 2 Celsius imply. We are already on plus 1 and counting, so we're getting there. So this is not an if, the discussion is what we need to do in order not to get there, or what are the huge efforts that we need to put in place in order to remain to 1.5 Celsius. A topic that's been pretty sensitive in our area is you know that during the last year, from 2014 and on, we've been discussing a lot in our country for the so-called refugee crisis. compared to what we expect in the next decades, that's a piece of cake, believe me. Just the difference between 1.5 to 2 Celsius implies a few more hundreds of millions of displaced people. That doesn't mean they will come to Greece, but they will try to move from their place to somewhere else. This implies a huge amount of instability in the planet at all stages. So it's not business as usual, it's business totally unusual. We don't have a recipe for that. I told you before that 2030 is key. See the curves and see in the right side of the diagrams. Of the diagram, see please the 2 Celsius and 1.5 Celsius different curves. They both need, in order to get there, we need to start immediately, and you see also a small delay in starting the necessary processes for radical change will have a huge result, result at the end. You move to huge differences at the increase of temperature at the end. But bear also in mind that if we keep on implementing what we have promised already, we're moving towards a 3.2 Celsius increase of temperature, which is catastrophic, and we know that. But keep also in mind that also links to what was said before. When we're talking about change, we should not value change anymore compared to what we have, but where we need to go and by when. That's what we need to have in mind. That's the theory. Let's take a picture of our reality. That's a snapshot of our national plan as put on the table, has been commented, as being, we know with Mr. Hamilton that we have different views on that, we've been exchanging that formally anyway. The thing is, no matter if you can, and we're both right, Mr. Famulus is right of seeing that as an ambitious plan, but this is not enough. It's as simple as that. To give you an idea, if you extrapolate the Greek plan, which is ambitious compared to what we have in Greece, as a global plan, that implies a 3.5 increase of global temperatures. We're not the globe, of course, but try to see the extrapolation to see how you can see things differently. And also, we are missing the 2030 key shift that needs to take place. Our plan depends heavily dependent on coal, remains free, it increases the... Okay, whatever, can do whatever.
You can take off the plastic.
Just move.
Okay, I think we can live with this small box on the left, that's fine. That was my problem. There is already more than 6 billion new investments in fossil fuel by 2030, excluding subsidies, and there's increased role of oil and gas drilling. I assume that, and I know the reasons why this is happening, but I'm saying that this is not coherent with changing drastically in order to achieve the 1.5 Celsius. What needs to be done? We need to avoid climate change risks to get out of control. We're going to have impacts, but we need to make sure that we avoid them being out of control. Science clear. We have 12 years to halve emissions in order to remain in the plus 1.5 zone. We need to cancel all investments in fossil fuels, and we need to move towards fast transition to efficiency and renewables. Somebody will say, but there's no money. But well, there's already money that's invested, that's been funneled towards fossil fuels. What we need to do is make sure that these are funneled to the right direction. And of course, as Minister said, we need to make sure that there's a fair transition. This is not impacting the weakest parts of the society. So we need to talk about redistribution of resources urgently, from fossil fuels to solutions. There needs to be structural change to economies, use of resources, consumption habits. Is not just, even the fuss of the last year about plastics, which by the way was triggered because of China blocking the import of recycled plastics from Europe. let's be frank and honest. It's not an issue of us becoming sensitive one day and waking up and say, oh, we're full of plastics. There was a reason why this has happened. There's also an opportunity to remember that plastics are produced through oil, and there's a correlation between the two. We need to get out of the single-use plastics full stop, for many good reasons, not just for the waste, but also for dependence of oil. And because of this not happening, there's a climate uprising that is already happening. Talking about money, I'm talking about the lack of money because all this is expensive. I think several of the previous speakers explained that the cost of renewables in nowadays is, if not cheaper, comparative to fossil fuels. And if you actually add subsidies, it's even cheaper in most of the cases. So you need to redirect this money. It's not easy, but we need to make it happen. And we need to see who's impacted and how we can balance and absorb this case. Currently, there is 1.9 trillion. I mean, just read that and go and Google that. It's great. The amounts of money that are currently invested, as we speak now, after Paris Agreement, on fossil fuels, show that clearly the economy has not dropped. I mean, the changes that we need to go through are not have not become the new paradigm, have not become the new reality. They are still marginal. They are still out there. We need to accelerate that. Oh, that's Greta. Yeah. Yeah. By the way, Greta was celebrating yesterday the Global Day of Awareness on Autism, because she's at the spectrum of autism. She's an Asperger person. And it's quite funny because this is a reply she gave. You know that Greta has been started striking last summer. She had to debate with her parents, then with her school, kept on debating. So a person on Asperger debating and explaining why that's already wow. And then there was an expected comment saying, well, kids should go to school. And then there was the reply of Greta that I love. Yeah, we hear you. We don't care. We need to make things done. And you didn't do it. Just. As a closing, I love this quote. I don't want you to be hopeful. I want you to panic. I want you to feel the fear I feel every day, and then I want you to act.
With his presence and his speech, we will now continue with, and thank you, Nikos Haralabidis. The last quote was really shocking, especially coming from a 16-year-old girl. Now I would like to invite Dr. Michalis Valachas. He's a professor here at Deree, and he's also the director of the Center of Excellence for Sustainability that is under the Office of Public Affairs, and he will talk to us about addressing the role of higher education institutions in the mitigation of climate change.
No, the other one. No.
Hi, I would like to welcome you to our conference on climate change. My talk today is going to be all about the role of the institution that you're all standing on, and by extension, all the higher education institutions. But I want to start the story with something that happened about 100 years ago in Professor Koudouris' alma mater. This is St. John's College in Cambridge. About 100 years ago, there was quite a level of turmoil from the student community onto the Cambridge infrastructure and the administration with one demand. And this demand was that the students should have been exposed and should have bathtubs. To that, the administration replied with all the good fidelity the following statement: why do the gentlemen require bathtubs? They've been here for 8 weeks. To us, in higher education, this is quite an astonishing thing, that there are so many things happen, and we, from our ivory tower of knowledge, and we have seen why it is an ivory tower of knowledge, it has produced so much research, it has produced so much education, but still it fails to address society from this perspective. 25.5% of the population, we regard climate change as the primary threat to future generations. But what I want to highlight in the bottom table is this 8.3%. This is the percentage of students that consider climate change a primary threat. And you would argue that when we're dealing with wars, when we're dealing with economic and financial difficulties, 8.3 might be reasonable. It gets lost in translation. But I want to highlight this slide. Whether you believe that climate change will affect or is affecting your life. Again, the numbers are staggering. By far, most of the student population does not believe that climate change is affecting their lives right now as we speak, or that it will affect them in the future. And these are students. These are people aged 17 and above. These are college students. These are university students. These are post-secondary education students. There is a problem. And we need to find a solution for this problem, obviously. But we need to see where we're going wrong with this problem. In 2017, the University of the Aegean conducted a survey on Greek universities and post-secondary education, and we saw the following thing. That out of all of the universities, only close 40% of these universities had a GHG, greenhouse gas, that is, reduction strategy. Only a quarter of these universities have a relevant climate change mitigation or adaptation policy. And from the 3 bodies that were assessed from the context of their syllabi, their context of the material they were delivering, from the context of their publications and research, we have that the climate change courses, they constitute less than 1%. The publications, from the total publications in the university, is less than 1%. And the outreach attempts towards the student body, towards the training of staff, and towards the outer community is about 2%. The problem that we saw in the previous slides is highlighted in 5 categories: operations, governance, curriculum, research, and outreach. Although the universities, they are producing by far the greatest amount of scientific research, although we are dealing with climate change as a fact, we are failing to convey this message to our communities. And unfortunately, the leaders of tomorrow and the offspring of our academic brethren, they will be not equipped to the degree that we want them in order to face climate change. And this is not the science-based community. These are the students that come from all disciplines. We're dealing now with students that come from business, from dance, from the fine arts, from any part of the curriculum. And they all need to be a target towards our understanding of what we interpret to be climate change. The anthropogenic and the fact of anthropogenic climate change. As such, what we try to do is establish a sustainability plan within the higher educational framework. And what we have seen is that the 5 domains that we mentioned previously, they have a certain hierarchy within them. And trying to analyze this hierarchy, what we do find is that governance can be subdivided into how an institution, a higher education institution, a college, a post-secondary education institution, finds its own institutional priorities, how it defines its values, and how it proclaims these values to the world. Education, beyond doubt, this is the major role of a higher education institution. And there we're aligned with changes that need to be incorporated onto the curriculum and our approaches to pedagogy. Climate change needs to leave the science classroom. It has to go into every classroom. And through campus operations, which is the usual suspect that when we regard an institution and try to see how we can better ourselves, we are always blaming, that through the reduction of emissions, through transit and through various policies, it also needs to go through this fine testing grounds that is student perception of climate change. Research, the undeniable role that scientific research has played and will be playing onto climate change, but finally and not least, the community outreach. Whether students become involved in climate change, whether they become educated on a peer-to-peer level to climate change, whether staff become educated again on a peer-to-peer level through climate change, or even from students, and how we approach the rest of the community. Universities, higher education institutions, they have a role. And this role is to prepare the community for these changing circumstances that we are about to face up until 2050, up until 2030. And we need to be clear in the way that we communicate this. What will follow now is our humble approach towards meeting with those goals. So we will start with the way that the American College of Greece at least tries to approach governance through its own institutional priorities and values, its education, its operations, its own research, and finally its community outreach. This is a very important thing. When we regard our SDGs, the Sustainable Development Goals, we see number 13 and climate action being a major one of these. And we do see the role that education and higher education, what is defined as the tertiary curriculum, needs to play within this great scheme of things. And our take on SDG 13. We have built a roadmap, and that roadmap depends on the 5 pillars that we were discussing about. It needs to be something that governance has to play a major role. And for us, and from our perspective, this is a strategic goal. Mitigating climate change, or the greater vision of sustainability, it is now something that we have deeply in our roots and the way that we approach all of our institutional priorities, and through our values, our all proclamations. In 2018, we were awarded the Star Silver ranking as a recognition of our efforts towards sustainability. But for me, the other ranking of the holds a little bit more value. The Sierra Club was the first environmental organization in the United States and probably worldwide. It was founded 125 years ago. And in 2018, we were awarded, because of our efforts towards the mitigation of climate change, our efforts towards sustainability, the cool schools, or being listed as one of the cool schools. And through our roadmap on education, we do have a major on environmental studies. We do have minors on both sustainable tourism and, as shown here, on environmental management. But most of our work is done through liberal education. Our approach to knowledge. And what is that? That is our approach in having every student be exposed into at least 1 or a full year of science-based courses. And this has led towards this percentage. At least 1 out of 2, or 50% of our students are graduating having taken at least 1 course that contains within its learning outcomes climate change. When we magnify that and we consider the number of sustainability-related courses that we're offering and the courses that are involving climate change, we are trying to put forward this notion of this ever-changing perspective in the climate into the heart and soul of each of our graduating students. And we try to do that through incorporating our facilities, using the campus as a living laboratory. This is a key process. We have our building facilities, our infrastructure, the mountainside campus that we're living in, acting as a laboratory. Laboratory for research, laboratory for student-driven research, and as we will see later on, as a breeding ground for student science, for citizen science. Campus operations. This goes beyond mentioning that we try to achieve a carbon neutrality to the best of our efforts. We have, for the first time in our history, conducted a greenhouse gas emission protocol. Our roofs, including the roofs that you do see around you on this library, are green roofs. And we're trying to mitigate climate change through these very humble steps. But using these steps, we train students. Our greenhouse gas emission protocol, it involved the work of students. Our green roof, it is a course that Cristina Marulli, the founder of the Center of Excellence for Sustainability, designed in order to train not only the internal community, but also the widespread community about this potential tactic. And we do that through energy saving, whether that is through reduction in our printing through various platforms, whether that is the technical services offering their enlightenment and helping us facilitate this. And we try through our entire curriculum to incorporate campus operations as a solid part of it. Right now, Dr. Apostolaki is teaching a course that is called Greening the Campus. And this is a course that tries to incorporate these campus operations into how our campus is evolving. And our community outreach. We're dealing now with students and staff being continuously exposed to climate change and the ways to mitigate this climate change, either through citizen science, by organizing bio-blitz and forming essentially the backdrop on which we can measure climate change occurring onto our neighborhood, which is the slopes of Mount Enemitos, or through student synergies between, for example, this image over here is from the Environmental Studies Society and its synergy with marketing to grow a herb garden, and through that try and find out many, many different things about not only growing stuff, but also trying to sell them to the community. We'll keep you posted on that when you want to buy a pot of oregano for 10 euros. And we are also doing that through collaborations. And our collaborations with the Navarino Environmental Observatory and our collaborations with SPY are key collaborations where we're trying to bring down the curriculum not only to the baseline of the students, but also to try and incorporate that to the widespread community. In essence, what we really want to do is take out climate change from the blackboard and always and never deny ourselves the thought of the bathtub, even though the bathtub in this case might look something like this. Thank you.
Thank you, Dr. Valderhaas. Now I would like to call Professor Andreas Papandreou, who is a professor of environmental economics at the National and Kapodistrian University of Athens. He is also a co-organizer of this event. He is the co-chair, the other co-chair of the United Nations Sustainable Solution Network, alongside with Professor Phyllis Koundouri. They've been great in assisting us in organizing all these events. So Professor Papandreou will talk to us about the economics of climate change with a focus on Greece. He was involved in developing the reporting for the economics on climate change on behalf of the Bank of Greece. He will tell us more about it, of course. So, thank you.
Thank you very much. Let's just make sure I'm that direction or the other direction. Right. Okay. There we go. First, again, as co-organizer here, I would also like to thank Claudia Karidis and Stella Apostolaki and the American College and the entire team of people that have worked to make this possible. I have to say I was also extremely impressed with the presentation you just gave about the work that the college has done on sustainability. And we really need to emulate that example in our public schools. And of course, with our connection through SDSN, we really have to start working on that immediately. So I'll say a few things about the economics of climate change with a focus on Greece. Let me just say that already there have been a number of points made from the previous panelists that have to do with economics of climate change. So they've done part of my work for me. When my students. As Phoebe, we still have the academic background, so we are influenced by that approach. Students are kind of surprised that there's something like environmental economics. Don't environment and economics clash? Aren't they the opposites? And then I say not only environmental economics, climate economics. Now we have climate economics. Well, how is that possible? Well, one has to realize that yes, we get all the information from the physical sciences. We can't do anything without knowing about the ecosystems and the broader environment. But if you ask the physical scientists who's at fault for the problems that the world is confronting, they say anthropogenic. And what does that mean? It's the economy, stupid. So I start with, if we really want to understand the causes of both climate change and broader environmental issues, we have to understand what's happening in the economy. So I start with three questions and across three dimensions to give a sense of the central issues that economists are involved in. Why does the economy fail to protect the climate? So what's happening? Why does the economy not able, the market system, the state system, whoever's involved, do adequate job in protecting the climate? The climate is clearly one of the most precious services that's providing in terms of temperature for the world. Now, a very quick answer, but it's only a very small part of it, is that we treat the environment and the atmosphere as a free resource. It's our dumping ground. And we know that if we don't get the consent from someone to use something, we don't have to pay for it, we don't take care of it. So that's the first way economists will look at that issue. A second question is, what level of climate change should we aim for? So that's something that economists look at. How do we decide the 2 degrees, 1.5 degrees? Now, as it happens, this has been decided more by the physical scientists and less by economists, and often they give us the cue, and we try to see what we can do within that range. A third question is, once we know what's wrong with the economic system, once we know what we should do to improve the situation, what policy tools should we use to achieve the goals? So that's the third question. And now, these questions apply to the many dimensions of the climate change problem. The one is mitigation. How do we reduce emissions so that we avoid climate change? So we actually achieve the target of 1.5 or 2 degrees Celsius. And the questions apply to all these. Adaptation. If we know that the climate is already changing, that's having an impact already. We're seeing it in the major climatic events, the weather events that we're going, the fires, the droughts, the floods. What do we do to adapt to these changes? Is the economy doing enough to adapt? What are our policy tools to improve that? And the third question is, well, if we actually manage to eventually convince the world that we have to move as fast as we have and really make the transformation that we need, how do we ensure that each of our economies adjusts to that major transformation, that revolution in the energy system? Now, this is kind of a picture taken from the Nicholas Stern review in 2006. It's important because it was really the first study that kind of, to a broader public, put the economics of climate change on the map. And it gives you a sense of the potential impact of changing temperature resulting from climate change to the various areas that, of course, are part of our lives. And what economists usually do is they look at these various impacts and they try to calculate the costs, the damage in terms of monetary amounts, because unfortunately many people only think in terms of money. And so we sometimes have to make that calculation. And also what benefits we have and see how we balance. The benefits, of course, is we use cheap energy sources like lignite. That means our transportation, at least historically, was cheaper than cleaner forms of energy. But making that benefit cost analysis, we try to determine what's the right action and how fast we have to move. That's just to give you a sense of what we're doing. That's in part what we did in the Bank of Greece study, which I'll come back to in a minute. Now, there are basically two ways of thinking about, from an economist's perspective, about the issue of climate change and mitigation in particular. One is to try to measure the benefits and costs that we've done. And what we do is we take what is the most likely path of the world if we take the business as usual. What if we actually take action to mitigate, to reduce emissions, and therefore reduce the impact, and again measure the benefits and costs of the most likely central path of this analysis. And as we see here, the central prediction of the IPCC 2014 is without catastrophic loss of ice sheet, we should expect that, for instance, the sea level rise will be about half a meter forecast by the end of the century. Now that's not a little. Think of our coastline and think of a meter rise in the sea, what impact it will have on our coastline, on our tourism. But in fact, there's another way of looking at the climate change issue. And again, it's an economics perspective. It's an issue of insurance. Instead of looking at what's the most likely outcome, why don't we think about what happens if things go wrong? The less likely, but not impossible, in fact, actually a fairly decent probability of this happening. In fact, fears about climate are based to a large extent about these worst case scenarios. For instance, complete loss of Greenland ice sheet would cause 7-meter rise in sea level in the world. I was just discussing, we just had the Convergence conference the day before yesterday, and we heard that if all ice over land melts, we're talking about 70-meter rise of water. Now, yeah, I mean, so these are catastrophic impacts. Now, if we think of things in terms of insurance, think about, people care a lot about unlikely worst cases. We do that in our real life. How much time do you leave to get to the airport on time or to come to this conference on time? Airport security is all about worst case possibilities. Insurance is not based on averages. The average U.S. house has a fire every 250 years, which is 0.4 probability per year of a residential fire. But almost all Americans have fire insurance. Probability that an American will die next year is less than 1% until age 61. But most young American parents have life insurance. We care about these potentially low probability but catastrophic events. Just think of this. Probability of enough warming to guarantee the loss of Greenland ice sheet is much greater than 1%. It's not a low possibility. 1 in 100 will have a 7-meter rise in sea level. So should we buy insurance for the planet? Yes, we should, absolutely. That's the key motivation. Now, just in terms of some of the things that were said earlier again, the national commitments that derive from the Paris Agreement, 2015, if fully implemented, are not enough to achieve the goal lower than 2 degrees or 1.5 by the end of the century. That has also been said by Charalambidis from Greenpeace, and others have pointed to that. On current trend, we will hit 3.2 and possibly more by 2100. While global emissions were constant for 2013 to 2016, and they gave us some hope that maybe we're doing something, we're decoupling the economy from the emissions, they surged in 2017 to 1.6, and we have a record high for 2018 of increase in 2.7. So things are not looking good. Now, it's worth looking a little bit at the history of the kinds of transitions, because basically what we're facing is a major social-technological transformation of our society and our economy. So why don't we look a little bit at the past and see what information we can get. By and large, we can say that since the Industrial Revolution, there are about 5 major socio-economic technological transformations. The Industrial Revolution in Britain was a period where cotton started becoming a major source of advancement. And in terms of transformation, there was canal mania. The British were first in taking the leap there. Second major transformation, age of steam and railway mania, Victorian boom. Again, the British were on the forefront of these transformations. Third transformation is the age of steel and heavy engineering in Britain, USA, and Germany, electricity. Fourth, the one we're probably most familiar with in terms of our recent life cycle, right, is the age of oil in the autos, oil industry, automobiles, and so forth. And fifth is the information communications technology revolution. The question now is whether we're going to move to the sixth, and what are the implications of the sixth sustainability revolution that we have in front of us. Now, what are the main lessons we can take from these past transitions, and in terms of what our present challenge is? Now, the grand patterns characterized in the past technological transitions is usually the key driver of the transition was some new application, some new good, some new service, an end-use application that was attractive to consumers or to producers that drove the transformation. In fact, it was more better services than prices. The automobile was more expensive than the horse and carriage, but it had a number of attractive features that the horses did not. Lighting, electricity, light bulbs were more expensive than candles, but they had a number of attractive features. And they drove the revolution. Transition in all these cases took decades to sometimes over a century. And they involved far-reaching changes across different dimensions. Just to look at roads, you have to think of service stations, traffic rules, housing, and so forth. Someone was just telling me, it's great, I was reading recently that Elon Musk with Tesla is doing a great job with the electric car. But it's still being purchased mostly by wealthy people. And one very simple question is, people have garages, they can plug it in. What happens to all the people that don't have garages? Where do they plug in their car? So that just gives you a sense of the kinds of issues and problems you might have in this kind of transition. Now, the major departure for our sustainability transition are the following. First, there isn't some attractive service or good that's going to move this transition. The only good is that we're going to protect ourselves today and in the future. So there isn't a consumer market to drive this. So it has to be largely policy-driven. And that's an important departure. Secondly, we can't simply wait for the revolution to take 50 or 100 years. We have a very short window. The 1.5 degrees Celsius target, if we're going to reach it, IPC says we have a window of 2 years to act. If we spend more time, we're going to the 2 degrees and longer. And the third main challenge is we need global coordination. This has to happen across all countries. We can't simply wait for Britain to do the revolution and the rest to follow, or the America with the car to do it. We have to all do it at the same time. So it's a huge challenge. Now, how am I doing in time? Anyone keeping track?
Well, anytime you're ready, how much do you have?
And I would like to spend another half hour. Okay. Another 5 minutes. Okay. So I'll move a little faster, speed up with the talk. One of the interesting issues that economists have been confronting is economists have always been saying we need to price carbon emissions. We need to, but exactly because we're treating the atmosphere as free, we don't take into account all the damage done by these emissions. And it's a fairly simple idea. Tax carbon emissions, and then we'll know that anything that has high content of carbon will avoid it, will be pushed to other forms of energy. And yet why it's politically difficult to attract. We saw Macron with the yellow vests had difficulty because he tried to make a small change in the energy price, and there was a reaction. Now, there is a way out of that. The economists, in the largest public statement of economists in history, 27 Nobel laureates, 3,438 economists suggested a carbon tax, but also that all the revenues are returned per capita to individuals. So that would make the public want the carbon tax, okay? Because we get a check from everyone's use of these forms. And then there's also the Green New Deal, which says regulation is the way. Since I have a little time, I'll just say that we need both carbon prices and regulation. We'll make certain automobiles more expensive, but we also need a regulation so that electricity can be plugged. We can find a garage to plug it into. And I move beyond. This was basically said from the president of the Bank of Greece, Stournaras. This was our Bank of Climate Change Impact Report. It gave a sense of the potential damage of climate change. As I said, this is the most likely outcome. It's not the worst outcome. 700 billion is actually small relative to some of the worst outcomes, the catastrophic outcomes. So let me just say that in terms of Greece's own attainment of the goals, it's expected to actually achieve its 2020 emissions reductions and energy efficiency targets agreed with the EU. One of the main reasons it's going to achieve this, on the negative side, is the economic crisis. If we have lower growth, we use less energy, we have fewer emissions. So one of the reasons we're successful is our failure. The other reason we are successful is, in fact, the fact that we have done a good job in supporting renewables and energy efficiency, and in that regard, we're both on target and above target. And in terms of our future target of 2030, the question is, when the economy bounces back and we start again growing and using lignite and other forms of oil energy, and our emissions increase, will we still be on target? That's the question. Shall I close it? Okay, I close it saying this is the good picture, which is our renewable energy. This is the negative picture for Greece, which is our intensity. We're, in terms of our GDP, look at how low we are in terms of the intensity of carbon emissions and carbon content in the energy. Of course, that's largely the lignite. And just to leave you with a question that our friend from Greenpeace mentioned, we're all enthusiastic about, at least most Greeks seem enthusiastic about hydrocarbons right now in Greece. It's not a simple question. Of course, it would give us energy security, it would help us pay our debt, but we need to think about whether, if we are going to make the climate change transition, whether we're going to actually be able to use the resource. It's going to take once we find them, it's going to take at least 10 years to start exploiting them. And we have to find out about whether they're exploitable, what the price of energy is going to be if we actually attack climate change. It is my hope that we reach a stage that we actually have to leave most of that energy in the ground. Thank you.